Let's now have a look at the simple quantum protocol for position verification. As usual, we will describe what the honest parties should do before worrying about security. So let's assume that Waldo is, for the moment, honest, and Alice and Bob want to verify his position on the line between them. By now, you're probably not surprised that we will design a protocol using BB84 states. These are indeed very nice. We know how to prepare and measure them very well by now. And no quantum storage will be necessary to execute the protocol. So how does this protocol go? Before the protocol starts, Alice and Bob secretly agree on a random string x of length n. So x is x1 up to xn. They will also agree on a random basis string theta of length n, where we again associate theta being 0 with the standard and theta being 1 with the Hadamard basis. I will draw the communication of Alice and Bob into the space-time diagram, so we can see the timing of the messages as well. As you might have guessed, Alice now prepares the string x encoded in the basis theta and sends it to Waldo. So if theta being 0, she sends the bit in the standard basis, so either 0 or 1. And if theta is 1, she sends the bit in the Hadamard basis. Alice and Bob will time the messages in such a way that Alice's qubits and the bases that Bob will send to Waldo arrive simultaneously with Waldo. Or indeed, the basis arrives not later than the qubits. Waldo, being of course at the claimed position now, measures each bit in the basis theta. So the first qubit she measures in the basis theta 1 and so on. There's no noise here now, so this means that knowing the basis, he measures each incoming qubit in the correct basis to learn the string x1 up to xn perfectly. Waldo then returns the string x as proof of his position to both Alice and Bob. Now Alice and Bob check whether the transmission tilde x, some string that Waldo sends to him, is really equal to their chosen string x. If not, they immediately accuse Waldo of cheating. Alice and Bob now also verify the time at which they made the transmission. So in addition, what they're going to do is they're going to check the timings. If Waldo is at this particular position, there will be a particular time that both Bob and Alice expect a reply at. This is our protocol for position verification. Let's first check if the protocol is correct. And this we have already alluded to. If Waldo is at the right position, he can indeed learn x, since he has both the qubits and the basis information. If he would be a little bit further this way, he could not have received the basis information when the qubits arrives. There are also no unforeseen message delays here, because remember that if he sends information to Alice and Bob, Waldo, honest Waldo at least, is guaranteed that it really arrives after this particular time. So this means that if he honestly measures the qubit, the basis, he will also pass the timing check. So what if Waldo tries to cheat? In particular, what if Waldo and Wendell collude to trick Alice and Bob? It turns out that if we make no assumptions, then our protocol is actually not secure. They can indeed lie to Alice and Bob. I will show you an explicit attack using quantum teleportation shortly. Don't worry if you have not seen quantum teleportation yet, then the next video will give you an introduction. Otherwise, you can skip right ahead. At the end, we will see that if we limit their storage, or if we limit the entanglement between Waldo and Wenda, then security can be achieved by just sending sufficiently many qubits.